Jan Copley's example 4.3-2 Heat loss from an insulated pipe. A thick-walled tube of stainless steel having a conductivity K of 21.63 watts per meter Kelvin with dimensions of 0.0254 meter internal diameter and the outer diameter is 0.0508. Okay, it's covered with a 0.0254 meter layer of asbestos, meaning it's being lagged, or meaning it's being insulated by asbestos with conductivity of 0.2423. The inside wall temperature of the pipe is at 811 Kelvin and the outside surface of the insulation is at 310.8. So meaning the inside of the pipe is quite hot. That's why we insulate it so that we could minimize heat loss. For a 0.305 meter length of pipe, calculate the heat loss and also temperature at the interface between the metal and the insulation. So let me draw a rough sketch for this first. Okay, here more or less this is like this, like the red one is the steel and the green one is the insulation. And this case, heat transfer will flow, of course, it's high temperature. The fluid inside this pipe is quite hot. This point here, the temperature, let's call that temperature T1, okay, or Ti, the inner temperature, and that inner temperature is quite hot. What's Ti? Ti is actually equal to 811 Kelvin, the temperature inside the pipe. Temperature outside, this at the surface, is actually quite, well, it's at 310 outside the insulation. This is T out, okay? T outer is actually 310.8 Kelvin. And, well, we have actually the heat flows to different types of material. The first shell is made of steel. The other one is made of insulation asbestos. So essentially here we have resistance in series, but the difference now is that our flow is through variable area and through cylindrical area. In this case, we are just asked to calculate for the heat loss. So what is heat loss? So very simple still, the approach will just be we're using the very generic equation for heat loss. Q will just then be the driving force, in this case delta T, the difference in the temperature, Ti and To, okay, over the resistance. In this case, we have resistance in series, so we still just simply add the resistances because if they are in series, then the resistance will just simply be added. So the only problem is how do we determine the resistance, okay? Now, to calculate for the resistance, we're using the equation. To make the analysis simpler, we'll just label this now. Instead of Ti, let me label this as T1, okay? T1, and the outer is the in between, the temperature at the interface, let me call that T2, and the temperature at the outer surface, let me call that T3, okay? We'll have here, this radius will be called R1. The other radius, which is actually from that till the end of the steel pipe, we call that R2. And then the other one, which is from that to the green, meaning to the outer surface, we call that radius 3. Okay? So that we could just simply label them and put values to it directly. So now, what is R1? Let me put values first for R1. Well, R1 is simply, let me put R1 here. R1 is simply what? The inner radius of the steel, the stainless steel, okay? So the radius of that will mean half of the diameter, right? 0.0254 divided by 2, so it gives me 0.0127. Okay? Now, R2 will be the outer radius of your stainless steel tube. So in that case, the outer radius will just be 0.0254 meters. How about R3? Well, it says here that it's being insulated with a thickness of 0.0254 meters layer of asbestos, adding 0.254 of it. Wow, it's quite thick, right? The drawing really is not drawn to scale, but R3 will be now equal to 0.0508. Okay, 0.0508 meters. Well, other information we need is the conductivity, right? So for for the steel, we must know its conductivity, and also for the asbestos, okay? Okay, there for the steel we have 21.63 watts per Kelvin conductivity, and the asbestos is quite low. That's why it's used as an insulation, 0.2423 only. Now, I think we are ready to calculate now for our resistances, right? Delta R, K, area log mean. Oh wait, area log mean first. To compute for the area, how do you compute that? What is the area this one, of the inner area of your, looking first at the pipe, steel pipe. So let's focus first on the steel pipe. For the steel pipe, the inner area will of course be the area 1, which has what? Two, with this radius R1. That's 2 pi R1 times the length of the pipe. Well, the pipe is not given, we are given with the length 0.305 meters. Okay, that's what we're looking for. What will be the heat loss per 0.305 meter length of a pipe? So times L here. That's the area here for the inner area of your steel. For the outer area of the steel will be the area 2, in this case 2 pi times the radius 2. That's the outer now area for your steel, R2 times L. Okay, and computing this one, this will give us some values. The inner area, or area 1, is equal to 0.0243 meters squared. And outer area of the steel pipe, or area 2, is equal to 0.0487 m squared. And now the area log mean for this steel pipe will simply be what? Area O minus area inner of for that steel pipe over ln of AO over AI. Okay, and direct substitution with the values will give you 0.0351 meters squared. Okay, now that's only for the steel pipe. How about now for your insulation? Let's now try to take a look on our insulation. Let me drag this down a bit. Inner area for your insulation is actually equal to A2, like the outer area of your steel pipe, right? So that's just A2, and we know the value of that, right? That's just 0.0243 meters squared. How about the outer area of your insulation? This one, okay? So it's now with radius R3, and to calculate for that, it's simply 2 pi times what? R3 times L. Well, R3 is 0.0508, L is 0.305. You do the math, and then that will then be equal to 0.0974 square meter. Okay, so that's the outer area. Now, of the insulation. Now, what will be the area log mean for your insulation? Well, simply area outer minus area inner. So that one divided by ln of that. So use the same formula. We'll just simply have here area log mean equal to 0.0703 meters squared. Okay, so now I think we are very much ready to compute for the different resistances for this. Okay, so since the formula is this one, we can then simply, I think, compute for what is the resistance for asbestos, what is the resistance for the steel pipe. Okay, so now let's try to compute for the resistance of the steel pipe, resistance of this asbestos insulation. Now for the steel pipe, the resistance R for the steel pipe just be equal to delta R. What's delta R? The thickness of the pipe. What will that be? Well, R2 minus R1, okay? That's delta R. K, we know the K. K for the steel pipe, it's 21.63. K for the steel pipe, and area log mean for the steel pipe. We know that. Area log mean for the steel. And it's equal to this one, 0.0351. And if we compute that, we do the math, that will give us 0.01673 Kelvin per watts. Similarly, if we do that for the asbestos, we do the same thing. The thickness of the asbestos is simply R3 minus R2. Well, the asbestos is also given. The thickness is also given to be 0.0254 meter thick, so you can use that as delta R divided by the K for asbestos, the conductivity, quite a low conductivity, 0.2423, and the area log mean for asbestos, it's equal to 0.0703 meters squared, and that gives me for asbestos 1.49 Kelvin per watts. So, since we are looking for Q, the heat loss, and it's equal to delta T, the temperature difference over the resistance, in this case, just the sum of these resistances. As you can see, the resistance offered by this tailpipe is very, very small compared to the resistance offered by the asbestos. Of course, the asbestos is the insulation in this case. Now, delta T, we know delta T, and we know R already, the sum of that. If we sum that, that's the R total. So we can compute now for the Q. So in this case, delta T, what's delta T? Well, the inner temperature is 811, the outer is 310.8. That gives me 500, okay, 500.2 Kelvin. And how about the total resistance? You simply add 2 because they are in series. So resistance in series, the total resistance will just be simply added. So 0.01673 plus 1.49. That gives me 1.50673. The unit here will be Kelvin per watt. So the Kelvin will cancel. And finally, I'm getting a Q equal to a value close to 332 watts. Okay, so that's the answer, meaning the original question simply asked for calculate the heat loss. So meaning, well, in every 0.305 meter length of that pipe, you are actually losing 332 watts of heat, meaning every second 332 joules of heat energy is leaking out of the pipe. Anyway, that's with the insulation already. Well, as if there's no insulation, we expect that it will be much greater than that. Now, the other question is, what is the temperature at the interface between the metal? Like, what is this T2? The temperature between this red and this green. Well, to solve for this question, to look for T2, or looking for T2, well, we could just take a look, focus on this red, on the steel. Or it's up to you, either you focus on the green or you focus on the steel pipe. Now, if you focus on the steel pipe, you know that through the steel pipe, the flow of heat is up to 332 watts, meaning that same amount of heat will flow to the steel pipe and also to the insulation. But now we're looking only in the steel pipe, and if we look at that, we can still write that Q is equal to delta T over R. That still applies to the steel pipe. But this time, Q is still the same. Well, the overall Q is the same as the Q that passed through this steel pipe alone because they are in series, okay? Meaning the Q that passes through here is the same Q that leaves the surface of the insulation. Now, delta T in this case, since we're only focusing on the steel pipe, will be temperature difference within the steel pipe, the inner steel pipe and the outer layer of the steel pipe. So that will be what? T2 minus the inner layer or the inner surface of the steel pipe is Ti or T1. It's 811. Well, since I know that T2 is smaller than T1, let me write the T1 first, okay? Because we know that heat will flow from high to low. So I'm writing here 811 minus T2, which as of this moment, I don't know. That's what I'm looking for. Well, the resistance of this steel pipe, we know already, right? Because the resistance of the steel pipe, well, let me drag that a little. It's equal to 0.01673, okay? And Q is equal to roughly 332 watts. So close to that. Now, and then I only have one unknown, T2. So I can solve for T2 using this equation. 332 is equal to 811 minus T2 over 0.01673. And in that case, that will give me T2 equal to, T2 will be 805. Roughly 805, close to that, 805 Kelvin. So as you expect, well, there's only a very small temperature drop, like 811 yung inside temp, but the outer shell of your steel pipe is just 805 because it has also very low resistance. Now, other approach in solving for T2, well, you can look at or you can prioritize the green one, the insulation. In this case, well, Q is still the same. The Q that flows through that green is equal to the same Q because this is what? In series. Now, if you do that, well, the green one, well, T2 will have a higher temperature than T3, right? T2 is what? That's what you're looking for. T3 is, that's the surrounding, the surface temp, and it's equal to 310.8. So let me do that. 310.8 over what? What's the resistance of this? We're focusing on the insulation. Resistance of the insulation is 1.49. Actually, it's 1.491, but let me just put that here, 1.49. That must be equal to same Q, 332. And do the math for that. That will give me 805. The decimal places is actually problem with some rounding off. This is Kelvin, okay? Rounding off errors that I committed somewhere. Okay, so the same approach, a different approach will lead to the same answer. So as you can see, there's a lot of temperature drop between the insulation. And inner insulation, the temperature is 805. The outer is 310. Meaning there's a lot of drop because the resistance is very high. Okay, that's it. Thank you.